Okay, hello everybody. Let's look at the second section of chapter 1, which is talking about hydrostatic pressure and force. First of all, we just learned what is the pressure. So for now, we just know what is the pressure and what is the force. And the force divided by the area means like the pressure. But what about the hydrostatic pressure? So first of all, if you just look at some of the hydraulic structures in this figure, for example, if you look at the dam reservoir, like in here, or lug gate, or the flap gate, like this one, these are schematic figures, or dam is like a real figure, it looks like this one, or the lug gate looks like this one, or the flap gate, if we're just gonna look at this one, we have the force applied from the water side towards the wall, or towards the gate, this figure, or towards the gate in this one, or the flap gate. The flap gate is like a gate that's hanging around this hinge. So we can see these situations, and all the time you can see the force apply and act at right angles to the surface, either the gates, the dam wall, or whatever we have. So this is like the situations that we have. So let's look at like the hydrostatic pressure in a different way. If we look at the spouting can like this, that we have like a few holes, okay? And we're just gonna see what is the hydraulic jet leaving water out of this kind of like a can. You can see here the highest jet seems to be the weakest one. There's no like the pressure behind that. However, the lowest jet is the strongest jet, has got like more pressure in that. So it means intuitively that once you're just gonna go down, the pressure increase with depth. So that's with this kind of like the background. Let's look at the pressure logger. If you have like a pressure logger, and if you have like a different depth of the water in this kind of like the tube, like this one, you can see here once the depth of the water that measure the pressure is H1, the P1 compared to like the situations that with the depth of the water, above that point of the point of measurement is H2, which is denoted by P2. P2 is the pressure and depth of the water is H2. And for the situations that we have the height of the water column is H3, and the pressure is shown by P3. If you're just going to compare the pressure in these three tubes, we can say the pressure logger shows that for the P3 shows the highest one, and the P1 is the lowest one, and the ratio or the equality is that the P3 is greater than P2, and that is greater than P1. So if we look at this one in different way, so assuming we're just going to go with like a one quiz, and we're just going to we have like let's say in this figure we have 5 containers, and we're just going to see which one has greater hydrostatic pressure. Imagine we have a different surface and different area, and we're just going to compare the pressure. So that's like a one question that you need to answer. Which one or which container has got the highest or greatest hydrostatic pressure? So that's the question that you need to just answer through the quiz that we're just going to go through with the different software. We're just going to go through that with poll everywhere. So, and we can discuss it in our discussions later on. Another question is that if you have like two tubes, one is like the vertical tube, like this one, but the other one has got like an inclined tube, like this one. However, the vertical distance or depth are the same for both of them, but this one has got the angle, So we're just going to see which one has, and this one is like the smaller tube compared to this one. So the question again is that which one has got the highest hydrostatic pressure at the bottom, okay? And the question is the same for this one as well. What has got the highest hydrostatic pressure? The same, we're just going to discuss about the hydrostatic force of both pictures, this one and this one. So let's just move on to the next topic. The next topic in here, we just look at the hydrostatic pressure with the formula that we have, which is called hydrostatic pressure, which you might seen this formula, pH, or the pressure at the depth H is equal to rho GH. We need to just prove this formula. Let's just see how we can just prove that one. We're just gonna learn so far the pressure is equal to force divided by A, or the area. In the free wall, or like based on the gravity, we can just write F is exactly W, or is like a weight of the body, or weight of the water, divided by A. W can be written mg, as we said, because the weight of the water. M can be written based on the density that we learned before. M can be written is equal to rho V, if you remember from the density formula. Rho Vg divided by A, and A here and V here can also be written as the A times H, because the volume is equal to area of the base times the H is the height of the water body. And A from the numerator and denominator are cancelled out. And what do we have is the P, or the pressure, is equal to rho GH, density times gravity acceleration times H is the depth of the water. So in this case, we're just going to look at this differently. We say at the top of the water surface, the pressure is 0. If we're just going to go 1 meter below, if you're just going to put the formula here, rho is like the water, assuming that it is like 1,000, times G is the gravity acceleration is like the 9.81 times 1,000 times 1. So it's like the 9.81 times 1,000, it is like a 9,810. Accurately, it's like the 9.81 times 1,000 is like the 9,810 Newton per square meter, or Pascal. So that's the same for the 1 meter. If you're just going to go 1 meter below, so we're just going to have like a 2 meters height. So it is a 2 times 9,810, and so on. If you're just going to every 1 meter lower, we're just going to see like the times the depth of that to the water surface. And at the end, if you have like a depth of D is a D times 9,810 Newton per square meter. And as a result of that, if you're just going to try to just plot the distribution of the pressure, or the pressure intensity diagram, we're just going to see like that there's a linear increase of the pressure. And if you have like a gauge pressure shows that increase like the level in throughout the depth. And we're just going to see P is equal to rho GH at the top. At atmospheric pressure, the gauge pressure, or the gauge shows like the 0 pressure. At the bottom shows like the P is equal to rho GH. So if you just look at, we're just talking about like a gauge pressure. Look at the gauge pressure. If you have a gauge here, normally we have a gauge here, and it shows the pressure either in, normally any kind of like a pressure gauge shows internally in the like the bar, and externally in another units is called like, for example, PSI. This normal like the pressure gauge, you've seen it for like the inflating your tire of your car. You can see this one. But these two like the units are the pressure units. They are not for SI units, but we're just going to see PSI is the unit of the pressure in English units, but bar is the unit that we just normally use for the pressure as well. So let's see how it works. So the pressure gauge, so we're just going to show in here. However, we have another definition of the pressure that is called absolute pressure. What does it mean exactly? So imagine that we have like a mercury, we have a tube of the mercury, and we are at the like a sea level. We're just gonna make the like a tube upside down and put it inside the container of the mercury, and we can just put it at this kind of container. And once we're just gonna see the pressure from the mercury, which is denoted by Hg, is equal to the pressure of atmosphere. So the atmospheric pressure, just try to just push the container surface of the mercury, and the column of the mercury just has got the pressure. Once they're just going to balance out, the depth of the mercury is equal to the atmospheric pressure. So we can say And at the sea level, this kind of like the depth is equal to 760 millimeters or 76 centimeters. So that is called atmospheric pressure. So however, at this level, atmospheric at the sea level, if you have like a gauge, the gauge shows the 0. So the gauge pressure at the sea level shows 0. However, we have the atmospheric pressure, which is equal to 760 millimeters, which is the absolute pressure. So in that case, we're just going to say the absolute pressure all the time is equal to the atmospheric pressure plus the gauge pressure, which is shown by this kind of like the gauge that we have. So every time we're just going to have everything, we need to just add the absolute pressure to the gauge pressure. However, as the atmospheric pressure is everywhere is subject to atmospheric pressure, we don't need to mention it everywhere. But you need to know the absolute pressure or the atmospheric pressure is like this one, is equal to 76 centimeters of mercury. If we're just gonna see what sort of like the connection between atmospheric and absolute pressure, we're just gonna say the absolute pressure in here is equal to the gauge pressure plus the atmospheric pressure. So the absolute pressure is gauge pressure plus atmospheric pressure. So that's like a relationship that we need to just have all the time. And if you're just gonna like put the formulas here, the absolute pressure is equal to rho GH plus atmospheric pressure. So that's like a formula. Atmospheric pressure plus the gauge pressure is equal to absolute pressure. So that's the relationship in here that we have. In other words, if you're just gonna look at here, the atmospheric pressure normally at the sea level is as like the terminology agreed to just be equal to 1 bar, okay? But 1 bar is equal to 100,000 Newton per square meter. So this is like the things that we just need to understand. And that is also, we just said that this value is equal to 0.76 meters of mercury. That is fine. And this value, if you have like a tube of the water, that tube of water has to be equal to 10.3 meters of water. That's the reason. It's like but practically it's impossible to just have like a tube of like the 10.3 meters of water. And that's the reason that researchers and scientists, they're just gonna use the mercury. Why use the mercury? Let's just prove this one. So, okay, before going to just prove that one, let's look at here. The atmospheric pressure is like fixed everywhere to at any level. It doesn't change of the depth. So it's like a constant here, like a rectangular atmospheric pressure. However, if it's just gonna go to the depth of the liquid, we're just gonna see the gauge pressure increasing linearly, and we're just gonna have like a triangle here and trapezoidal like a shape for the absolute pressure. You're just going to see at the top is like water surface, it's like the atmospheric pressure, and at the end the absolute pressure is equal to atmospheric pressure plus any kind of like a rho GH that we have in depth. So if we just look at the value of like for example a tube of the mercury and the tube of the water, we can just write the equivalent formula for 2 points between the same level. And we're just gonna write the rho GH1, rho 1 G and H1 is equal to rho 2 GH2 between 2 types of the tubes. One is for mercury and one for the like the water. And if you're just gonna like to substitute all the like the parameters here, we're just gonna see for rho 1, for the density of the mercury is equal to 13,560 times G times the H, the depth is 0.76, which is equal to 1,000, is like a density of the water, G times H2. We're just gonna prove that what is like a 10.3 meters. If you're just gonna work out this kind of like a formula, you're just gonna see H2 is equal to 10.3 meters. So 10.3 meters is calculated in theory. So because in practice we cannot do this one by having had this kind of like a 0.76 meters of mercury. So that's the gauge pressure and absolute pressure for this session. Thank you very much.